In this lecture, we'll continue our discussion on the first law of thermodynamics. We've already seen in the previous lecture that the first law of thermodynamics introduces internal energy as a state property. In this lecture, we'll also introduce another state property that's called enthalpy. So what we've seen in the previous lecture is that the first law for a closed system states that if you have a closed system on which you do work and there is transfer of heat to the system from the surroundings, then there is a state property which we call as the internal energy, which changes upon doing work and transferring heat to the system in a way that if you take the system from state 1 to state 2, then the change in internal energy of this closed system is equal to the energy transferred to the system in terms of work and heat. So delta U equals to W plus Q is the mathematical formulation of the first law of thermodynamics. And recall that in our sign convention, we are taking work done on the system and heat transferred to the system to be positive. So till now, what we've seen is that we knew that we have pressure and volume as state properties, and these properties, that is pressure and volume, are known outside thermodynamics also. So we know this from mechanics. But from the zeroth law of thermodynamics, we've seen that there's another state property, which is the temperature. And note that this temperature is not the absolute temperature. So you can measure temperature by measuring change in some thermometric property of a substance. But to define the absolute thermodynamic scale of temperature, we need to go to the second law of thermodynamics. So the zeroth law introduces temperature as a state property, and now we have seen that the first law introduces internal energy as a state property. Note that all these properties are not independent. We've already seen that if we have homogeneous system of a pure substance, that means a pure substance in a single phase, then for a given mass of such a system, then we can describe the state of the system using two intensive properties. And because we know the mass, even if we have an extensive property, we can convert it into intensive property. So therefore, we have these four properties now: P, V, T, and U. Only two of them are independent. So we can take the internal energy U as a function of, let's say, pressure and volume. We can also take it as a function of temperature and pressure, and function of temperature and volume. So there are only two independent variables or state properties which we can vary, and all other state properties are going to depend upon these two variables. Note that the notation that we are following throughout the course is that we'll denote any quantity that is in lowercase letters such as pressure, or let's say V, that is the specific volume. So any property that is in lowercase is an intensive property, with an exception of temperature, which we'll denote as capital T, so that we do not confuse with lowercase t, which we'll use to denote the time, and uppercase will be used to denote, let's say, volume, which is an extensive property. Similarly, U, that is internal energy, is an extensive property. But recall that we can convert volume, and volume per unit mass is an intensive property, which is the specific volume. And similarly, we can say that internal energy per unit mass is the specific internal energy. And when we look at specific internal energy, because we are dealing with a unit mass only, then the specific internal energy will be function of two intensive properties, which could be T and V. It could also be temperature and pressure, and it could also be pressure and specific volume. And recall from the zeroth law, we've already seen that pressure, specific volume, and temperature are related with each other through an equation of state. In particular, we'll call this equation of state as the thermal equation of state. Now, let's elaborate the first law further. And to do this, let's consider this system on which we do work and transfer heat. And we know that the change in internal energy of this system is equal to the work done and the heat that is transferred to the system. And if the system is composed of only pure substance having a single phase, then we can describe the state of this system by, let's say, temperature and pressure, or any two independent variables. Now, let's say that in this process where we take this system from, let's say, state 1 to state 2, if we have this system in gravitational field and we'll change the elevation of this system during the process where we take the system from state 1 to state 2. So clearly, this equation will not be applicable. Why? Because there's a change in potential energy of the system. But we can rectify this equation by adding the contribution of potential energy, and potential energy, which we'll denote by PE, will be a function of this elevation, that is Z. And this elevation is measured from some standard reference elevation. So then we can correct our equation for the first law as this, where we'll say the change in internal energy, which is a function of temperature and pressure for a homogeneous system of pure substance, but it might be having multiple phases, then it will be function, or it might have other components or phases, then we can have more than two independent variables. And this is the change in internal energy. Plus, now we'll add the contribution of potential energy. So we'll say the change in the potential energy, and that is equal to the work done on the system and the heat transferred to the system. Similarly, if our system is moving while its elevation is also changing, and we are doing work and transferring heat to the system, then we can add the contribution of kinetic energy, which we'll denote by Ke. And kinetic energy is going to be a function of the speed. Then we can write or update this equation for the first law by having the change in internal energy of the system plus the change in potential energy due to change in elevation plus the change in kinetic energy due to the change in velocity or speed, and that will be equal to the work done on the system and heat transferred to the system. And these functions, that is PE, that is potential energy, we can easily express in terms of the observable properties, that is the elevation. So if you have a system of mass m and g denotes the acceleration due to gravity, then the potential energy would be mgz, and the change in potential energy would be mg times delta z. Similarly, kinetic energy we can write as half mu squared, where u denotes the speed. So the change in kinetic energy we can write as half m delta of u squared. That is, whenever there is a contribution of some another energy that we have neglected, we can always add that and fix our equations. Or in other words, we can write the first law more generally as the change in the total energy of the system is equal to the heat transferred to the system and the work done on the system, where this energy is sum of all types of energies, that is the internal energy that might be a function of temperature, pressure and other thermodynamic variables, then the potential energy and kinetic energy, and there could be other forms of energies that we can add. So the point is that we can separate the contribution of energies that correspond to this internal energy that corresponds to the molecular or atomic structure of the substance, and this is the internal energy includes the form of energy that is associated with the molecular and atomic structure of the substance, whereas these forms, that is the potential energy and the kinetic energy, can be described in terms of the macroscopic properties, and these are the forms of energy that are known outside the domain of thermodynamics. So even from mechanics, we know that the potential energy function and the kinetic energy function can be written as these. So these can be described in terms of the macroscopic observable properties. And note that if our system is changing elevation and its velocity is also changing, then the state of the system is described not only by temperature, pressure and other thermodynamic variables, but also the elevation and the speed. So you need to use all these variables to define the state of the system. So this equation, delta E equals to Q plus W, is the more general form of the first law for a closed system. And in fact, you can add more forms of energy over here as well. For example, if you have a nuclear reaction, then we can also add a term such as minus delta M C squared, where C is the speed of light and delta M is the change of mass of the system. And note that we have a minus sign over here because delta M is negative. So then if you include this term for, let's say, a nuclear reaction such as fission reaction, then you will have these additional term, and then again you can apply the first law of thermodynamics, where the left hand side now has the total energy and not just the internal energy. One important thing to note is that the first law of thermodynamics only gives us the change in the internal energy and also the change in kinetic energy and potential energy, and there's no way to give the absolute values of these energies, the internal energies and all other energies. In fact, we never come across something like an energy meter which you can put into a system and measure energy of the system. So these energies are just some mathematical functions such as this potential energy and internal energy, which we can calculate in terms of some other variables. And to assign values to internal energy, kinetic energy and potential energy, we need some reference states. For example, over here, if you want to calculate the potential energy, then you can arbitrarily take this elevation and say that your potential energy is 0 over here, and then your potential energy over here at this elevation z would be mgz. But I could have taken this reference state at some other elevation as well, and that would be equally applicable. So there's nothing like an absolute value of energy. We always measure energy from some reference state, and fortunately we are always interested in the change in energy, because on the left hand side of this first law we'll always have the change in energy. So if you know energy up to some additive constant, then when you look at the change in energy, any form of energy, then that additive constant cancels out. And these reference states where you define that energy to be 0 is helpful only for tabulating the values. Otherwise, you could define the energy up to some additive constant. So what particularly we are interested in is the change in energy. Therefore, let's look at an example. So the example is in fact related to the Joule's experiment. So let's say that we have a tank that has some fluid, it could be gas, and it is stirred by this paddle wheel, and we do work by rotating this paddle wheel, and we do work on the system. And let's say paddle wheel does 5,000 kilojoules of work to the system. And in this case, we do not have insulated walls, and in the process, let's say 1500 kilojoules of heat is transferred from the tank to the surroundings. Then the question is to determine the change in internal energy of the fluid. And we can say that in this case, we start with a steady state or a quiescent state where there's no motion of fluid, and we after stirring and we stop stirring, then we again attain an equilibrium state. So the only contribution to energy that we are interested in is the internal energy, because neither the potential energy is changing nor the kinetic energy. Then we can see that we are only interested in the change in internal energy. So if we go from state 1 to state 2, then we can apply the first law of thermodynamics. And now it is important to keep in mind the sign convention. So the work done on the system is taken to be positive. So here we are doing 5,000 kilojoules of work, whereas heat is transferred from the system to the surroundings, and our system is denoted by this dashed line. So heat is being transferred from the system to the surroundings, therefore it is negative, and this is minus 1500 kilojoules. Therefore the change in internal energy of this fluid is 5000 minus 1500, and that is equal to 3500 kilojoules. So what you see is that we are always interested in the change in internal energy, and we are never interested in the absolute value of energy or any form of energy. In fact, there's nothing like an absolute value of energy. We always measure energy from some reference state. Now there's one more thing to note is that, and it is very important to emphasize this, that we've seen that the first law can be described mathematically using this equation, delta E equals to Q plus W. But like all laws of thermodynamics, we cannot derive this equation. We've not derived this equation, although we've described how we have arrived at this equation and why we should have an equation of this particular form, but we haven't given any proof of it. In fact, we don't have any proof for the laws. The only thing we know is that, so none of the experiments contradict this statement of the first law and the statements of the other laws of thermodynamics, and all experiments support that. Therefore, we'll take this statement as a truth, but there's no formal mathematical proof of arriving at that statement. And if we were able to give the proof of this statement, then we would not have called it as a fundamental law. So the idea is that there's no proof for fundamental law. We'll take them as truth and base our discussions based on these fundamental laws, such as the zeroth law, first law, second law, and third law. So we have seen that the first law introduces the internal energy as a state property. So now let's look at another property called enthalpy. So what we've seen is that internal energy is a state property, and it is introduced by the first law. And before introducing first law, we don't have any knowledge of this internal energy. So the first law introduces it as the state property. Now, if we take this internal energy and we add to internal energy, let's say, some other properties. In this case, because U has units of energy and pressure times volume also has units of energy, so we can add these two terms and note that pressure is a state property, volume is a state property, so the product of these two will also be a state property, and sum of U plus PV will also be a state property. So sum of any state properties will also be a state property, but there are particular combinations of these properties that come into picture during thermodynamic analysis, and one such property is this H, which we define as U plus PV, and this is called enthalpy. Just like the internal energy, enthalpy is also an extensive property. And just like internal energy, we can also define enthalpy per unit mass. So if M denotes the mass of the system or the working substance, then H over M is denoted by lowercase h, and this is the specific enthalpy. So H, that is specific enthalpy, is defined as the specific internal energy plus pressure times the specific volume. So let's look at why we are interested in enthalpy, and we'll look at how this enthalpy comes into picture through an example, and this enthalpy we'll see that comes into picture again and again during thermodynamic analysis. Here we'll just describe one such process. So consider a control mass or a closed system. So here we have the cylinder which is fitted with this piston, and we have gas in this piston cylinder arrangement. And let's say we'll also put some mass on this piston. So this is a control mass, and let's say that it undergoes a quasi equilibrium constant pressure process. So how we can take this system, that is this gas enclosed in this piston cylinder arrangement in a constant pressure process, is that we can add heat to this gas, and while this gas expands, the mass of the piston and the mass that is kept on the piston remains the same. That means the pressure remains the same during this process, and if the process is slow enough, then we can assume that it goes through a series of quasi-equilibrium states, and therefore this gas will undergo a quasi-equilibrium constant pressure process. So let's say that we take this system from state 1 to stage 2. So on a PV diagram, this means that we initially had the system at volume 1, and while keeping pressure constant, we take this system to a higher volume. Now let's see what we get when we apply the first law of thermodynamics. So we have U2 minus U1 because there's no change in potential energy or the kinetic energy in this case. So the total energy change is just equal to the internal energy change is equal to the work done on the system and the heat that is transferred to the system. Now to calculate the work done on the system, we simply have work done is equal to minus P dV integral going from 1 to 2, and the magnitude of this work is simply the area under this path that takes the system from state 1 to state 2 through a constant pressure process. And constant pressure processes, we also say, are called isobaric processes. So pressure remains constant, so the work done on the system is minus P times V2 minus V1. So if we plug in this work into the equation for the first law for the control mass or a closed system, then we get U2 minus U1 is equal to Q, that is heat transferred to the system, plus the work done on the system, which is minus P, and P remains constant during this isobaric process, and we have V2 minus V1. So we can take these terms to the left hand side and we'll get U2 plus P times V2 minus U1 plus P times V1, and that is equal to the heat that is transferred to the system. And note that the pressure remains constant during the process, so this is P2 is equal to P1. So what we see is that we have this combination of properties U plus PV, which we have defined as enthalpy. So what we get is the heat that is transferred to the system during this quasi-equilibrium constant pressure process is H2 minus H1. That is the change in enthalpy. Therefore, heat transfer in an isobaric quasi-equilibrium process is equal to the change in enthalpy. Note that if the process is not isobaric, then this statement is not applicable, as only for an isobaric process the work is given by this minus P times delta V. You could also show that enthalpy comes into picture rather than looking at this finite isobaric process. Even if we considered infinitesimal change in the state of this gas, then we could have written du is equal to dq plus dw. This is the differential form of the first law, and this is dq, and the work done on the system is minus pdv. Therefore, dq is equal to du plus pdv, and because pressure is constant, we can write this as d of u plus pv, and that is equal to d. So this is uppercase u because we are looking at extensive properties, and that is equal to dh. Therefore, the heat added to a system during a quasi-equilibrium constant pressure process is equal to the change in enthalpy. Now, besides this specific process, we will see the use of enthalpy while discussing the first law for a control volume or open systems. With this, we complete our introductory discussion on the first law applied to a control mass or a closed system. And now we'll discuss in the next lecture definitions of heat capacity, and we'll apply the first law of thermodynamics to derive relationship between the different types of heat capacities.